Welcome to the deep dive, Generative AI Futures. For you, the curious listener, you hear terms thrown around all the time, right? Transformer, attention, alignment.
Yeah, constantly.
But if you really want to get past the buzzwords,
Hmm.
past the marketing hype, and actually understand what's powering this huge tech revolution, the models you use every single day, you really need to look under the hood.
Absolutely. And that's what this deep dive is all about. We've designed it as a, let's say, a comprehensive technical roadmap.
Right.
We're not talking about server specs or anything like that. We're
Yeah.
digging into the series of, well, pretty profound mathematical and architectural breakthroughs that got us from just counting words
Yeah.
to models that can reason and create in really sophisticated ways.
So the mission today is basically decoding that technical core, moving from, complexity to clarity.
That's the plan. Clarity.
Okay, so let's unpack this journey. It sounds like it's defined by, what, three big architectural shifts, and then this alignment part at the end.
That's right. Three main paradigm shifts, plus the crucial alignment phase. We'll start with that first foundational leap, how we went from just like discrete words to encoding them into these dense, meaningful semantic vectors.
Got it. Vector representations.
Then we'll tackle the era of sequence modeling. And crucially, confronting the big crisis, really, of the recurrent neural network, those vanishing and exploding gradients. It was a problem that, honestly, almost stopped early neural language modeling in its tracks.
Wow. Okay. And after that?
And finally, we get to the attention revolution. That's what gave us the parallel processing, the scalability, and ultimately these enormous models we see now. And then we'll look at how we actually tame these giants, using techniques like direct preference optimization to align them with human values.
Sounds like quite a ride. Let's dive in. Okay, so before we got these fancy vectors, you mentioned we were kind of in a linguistic dark age, dominated by n-gram models.
Yeah, you could say that. I mean, n-grams were the statistical workhorses for decades, right?
What exactly were they doing? How did they work?
Well, they were pretty simple, based on something called maximum likelihood estimation, or MLE. An n-gram model basically estimates the probability of a word, let's call it no dollar, just based on the few words right before it.
So like a bigogram looks at one word before, trigram looks at two.
Exactly. It's essentially just counting. How many times does this specific sequence of, say, two words appear, divided by how many times the first word appears on its own? Simple frequency counts.
Okay, that sounds mathematically reasonable for like local patterns, but you said it ran into huge problems.
Oh, yeah. Two catastrophic problems, really. Scale and context,
Scale meaning.
meaning sparsity. Think about it. Even with a modest vocabulary, maybe 30,000 unique words or so, if you try to model a 4-gram sequence of just 4 words, the number of possible combinations just explodes.
How many are we talking?
We're talking something like $7 times 1017 possible unique 4 grams. 7 followed by 17 zeros. It's astronomical.
Whoa.
And even the biggest text data set you can imagine, it's only going to contain a tiny, tiny fraction of those possibilities.
So if the model sees a sequence it hasn't encountered in training.
It assigns it 0 probability, which is bad. It forces the model to fall back on simpler, less informative assumptions, like just looking at the trigram or biggram instead.
And that connects to the context problem, overfitting.
Directly. Because it's only learning these local frequencies, it overfits like crazy to the training data. So if you train an n-gram model only on, say, Shakespeare.
It gets really good at sounding like Shakespeare.
Exactly. It mimics the local flow, the grammar, the word choices perfectly.
Mm-hmm.
But it captures absolutely 0 deeper meaning or abstract knowledge. Ask that Shakespeare model to write about, I don't know, stock market trends.
It completely falls apart.
Completely. It can't generalize because the local patterns are totally different. Generated Shakespeare text and generated Wall Street Journal text are just worlds apart.
Yeah.
There's no shared understanding.
Okay, so that statistical approach hit a wall. What was the breakthrough idea?
The breakthrough was really a linguistic insight, famously put as, you shall know a word by the company it keeps. Meaning isn't inherent in the word itself, it comes from its context.
Right. Meaning is context.
That simple idea sparked the vector revolution. Distributed representations. Instead of thinking of each word as just a unique ID number.
Like a one-hot vector, where Apple is just a 1 at position 5,000 in zeros everywhere else.
Precisely. Instead of that sparse, isolated representation, we map every word to a relatively low-dimensional vector, maybe a few hundred numbers, in a continuous geometric space.
And that continuous space is the key.
That's the breakthrough. Because now, words with similar meanings used in similar contexts like king and queen or running and jogging end up being placed close together in that geometric space. The distance and direction between vectors starts to capture meaning.
Which n-grams just couldn't do.
Couldn't even conceive of it. Now, the first models that really made this work, like Word2Vec with its skipgram and CBOW architectures, they were laser-focused on one thing: computational efficiency.
Why was efficiency so critical right then?
Because to learn good vectors, you need massive amounts of text data. Trillions of words. And earlier neural network language models, they had these huge computationally intensive nonlinear hidden layers.
Doing big matrix multiplications at every step.
Exactly.
Yeah.
It just wasn't scalable for the data sizes needed.
Yeah.
So skipgram and CBOW were designed very cleverly to simplify the architecture, to cut out that massive bottleneck.
Okay, break those down quickly. Skipgram.
Skipgram tries to predict the surrounding context words given a center word. So the training objective is basically find word vector representations that are good at predicting their neighbors.
And CBOW.
CBOW is the inverse, continuous bag of words. It predicts the current center word based on the sum or average of the vectors of the words around it in the context window. Bag of words meaning order doesn't matter in the context, just the presence of the words.
So they're kind of two sides of the same optimization coin, both pushing for vectors that capture context, but doing it really fast.
Exactly. They optimize for speed and semantic coherence at the same time. And this is where it gets really cool. The mathematical magic that emerges after training.
You mean the vector arithmetic?
Yeah. These vectors aren't just static points. They encode relationships as essentially linear translations in that geometric space.
Ah, the famous analogy example, king minus man plus woman equals queen, or something like that.
Well, the classic one is textvec Spain plus textvec France. You perform that vector arithmetic.
And the resulting vector, the point it lands on in the space.
It's closest to the vector for Paris.
Yeah.
The model has learned the capital city of relationship purely from text, and it can apply it like a simple geometric translation. It's incredible. It wasn't explicitly programmed with geography.
That still blows my mind, but it's not just analogies, right? You mentioned compositionality, adding vectors.
Yes, this is maybe even more profound. Simple vector addition can combine concepts meaningfully. Take the vector for Russia and add the vector for river.
Okay, what happens?
The resulting vector ends up closest to the vector for Volga River.
How? Why does adding them work like combining ideas?
It stems from the math of the training objective, particularly how probabilities are calculated. The objective function relates the sum of context distributions for two words to the product of those distributions. And multiplication, mathematically, acts a bit like a logical A and D.
So adding Russia and river vectors favors words that appear often in the context of both Russia and river.
Exactly. Volga River fits that bill perfectly. So the vector addition effectively performs a kind of semantic intersection. It's a beautifully emergent property of the training process.
Which explains why these embeddings became so useful for things like search engines, right? Finding relevant documents.
Absolutely. Relevance is all about semantic similarity and relationships. But, to make these vectors really work well, the dimensionality, the actual size of the vector, turns out to be really important.
Okay, so is it just bigger is always better, more dimensions means more meaning?
Not quite. It's more nuanced. There's a sweet spot, theoretically linked to what's called the bias variance trade-off.
Bias variance. Explain that in this context.
Sure. If your vectors are too small, too few dimensions, they can't capture all the subtle shades of meaning and context. The model is forced to oversimplify. It makes inaccurate generalizations. That's high bias.
Okay, and if they're too big?
Too many dimensions.
Yeah.
Then the model might start encoding noise or weird artifacts specific to the training data. It captures spurious correlations that don't generalize well to new text. That's high variance.
So you need to find the right balance. Just enough dimensions to capture the real signal, but not so many that you capture the noise too.
Precisely. And empirically, finding that sweet spot requires testing. I remember seeing studies showing the optimal size for skipgram on analogy tasks was maybe around 220 dimensions, but for GloVe, a slightly different embedding method, it was higher, maybe closer to 560.
So it depends on the specifics of the model and the task.
Absolutely. It highlights that building robust systems needs practical tuning. But the core takeaway is this: that leap from sparse, isolated word IDs to these dense, continuous, semantically rich vectors. That was the absolute foundation for everything that came next in NLP and LLMs.
Okay, so we've got our words represented as meaningful vectors. The next obvious step seems to be processing them in order, right? Keeping track of the sequence.
Exactly. And that brings us to recurrent neural networks, or RNNs.
They sound intuitive. Recurrent meaning looping.
Yeah, they have this internal loop or recurrent connection. The hidden state from processing one word, let's call it DIRT1, gets fed back into the network as an input when processing the next word, HD.
So it kind of builds up a memory as it goes through the sequence.
That was the idea.
Hmm.
It creates this dynamic system that can, in theory, handle sequences of any length and maintain context over time, a built-in short-term memory. These seem like the natural successor to n-grams for modeling language.
But there's always a but, isn't there?
There is. A big one. RNNs ran smack into a fundamental, almost catastrophic problem during training, something that nearly derailed the whole neural approach to language early on.
What was it?
The problem was gradient instability. When you train these networks, you use backpropagation, sending an error signal backward through the network, or in this case, backward through time along the sequence.
Okay.
And that journey backward through many time steps proved incredibly problematic. It led to two related issues: the vanishing gradient problem and the exploding gradient problem.
Okay, let's take those one by one. Vanishing gradient.
This was the killer for learning long-term dependencies. Imagine you have a grammatical dependency-like subject-verb agreement, but the subject and verb are separated by, say, 50 words of other stuff.
Right.
As that error signal tries to travel backward 50 steps in time, it gets multiplied by the network's weight matrices at each step. If the important parts of those matrices, their eigenvalues, are less than 1, the gradient signal shrinks exponentially.
So it gets smaller
Yeah.
and smaller.
Until it's effectively 0 by the time it reaches the point where the error originated 50 steps back. The network literally learns nothing about that long-range dependency. The signal vanishes.
It's like that game of telephone, right? The message gets lost. So simple RNNs just couldn't remember things far back in the sequence.
Exactly. They had a very short, effective memory. Now, the opposite problem was the exploding gradient.
Where the signal gets too big.
Way too big. If those eigenvalues and the weight matrices are greater than 1, the gradient signal grows exponentially as it travels back. The norm, the size of the gradient vector, becomes enormous really fast.
And what does that do during training?
It causes chaos. Mathematically, you can visualize the training process as trying to find the lowest point on an error surface, like rolling a ball down a hill. Exploding gradients are like hitting a sudden, incredibly steep cliff wall on that surface.
So a normal step downhill.
Becomes a massive leap that throws the optimization completely off track. The parameters go wild, the training becomes unstable, it might just crash.
Okay, so this sounds pretty bad. Vanishing gradients mean you can't learn long dependencies. Exploding gradients mean the training is unstable. How did researchers even try to fix this with just plain RNNs before inventing new architectures?
It tried some pretty clever, deep technical fixes, tackling each problem directly. For exploding gradients, the fix was actually quite pragmatic: gradient clipping.
Clipping, like cutting it off.
Basically, yeah. If the overall size, the norm of the gradient vector, got bigger than some predefined threshold value, they would just mathematically rescale the whole vector back down to that threshold size.
Just cap it.
Yep. It's a bit of a blunt instrument, but it worked. It stopped those huge jumps off the cliff walls in the air landscape and kept the training somewhat stable.
Okay, that handles the explosions,
Yeah.
but vanishing seems harder, right? It's about a lack of signal, not too much signal.
Much harder. To fight vanishing gradients, they had to get more sophisticated. They introduced a specific regularization term into the training objective.
Regularization, like adding a penalty.
Kind of. This term added a subtle pressure during training, encouraging the network's weight matrices, specifically the Jacobian matrices involved in backpropagation, to behave in a way that preserved the size, the norm, of the error signal as it traveled backward through time.
So you're actively trying to force the system not to shrink the gradient.
Exactly. You're fighting its natural tendency to converge toward states where the gradient dies out. But here's the really tricky, non-intuitive part.
Go on.
The very mechanism designed to prevent gradients from vanishing, which involves pushing the system away from certain stable points, or attractors, actually made it more likely for gradients to explode.
Wait, how?
Because by pushing away from those stable basins, you often end up pushing the parameters closer to the boundaries between basins. And that's exactly where those steep cliff walls causing explosions tend to live in the error landscape.
Oh, wow. So fixing one problem made the other one worse.
Pretty much. You couldn't solve vanishing gradients without increasing the risk of exploding gradients. So the solution was you had to do both. You needed gradient clipping and that special regularization together.
Okay, so a combined approach.
Right. They called it SGDCR, stochastic gradient descent with clipping and regularization. And they showed it could work even on really hard synthetic problems designed to break RNNs, like the temporal order task.
What was that task?
It was deliberately pathological. The RNN had to see two special symbols, maybe an X and a Y, separated by hundreds of steps of just random noise symbols, and then output which one came first, X or Y.
A pure long-term memory test.
Exactly. And SGDCR actually solved it, with 100% accuracy for sequences up to 200 steps long, and even better, it showed generalization. A model trained on sequences up to 200 steps could often handle sequences twice as long, like 400 steps, without much error.
So it proved the simple RNN wasn't fundamentally broken, just incredibly hard to train.
That's a good way to put it. It needed a very careful management of the gradients. But understandably, the community started looking for better architectures that could handle memory more intrinsically without needing such complex training tricks.
And that led to?
That led to the gated RNNs, LSTMs, long short-term memory networks, and later GRUs, gated recurrent units.
Ah, LSTMs and GRUs. Those were the dominant players for a long time.
Or almost 2 decades, really. They introduced these clever gates, input gates, forget gates, output gates, and a separate cell state that acted like a conveyor belt for information. These mechanisms allowed them to explicitly control what information to keep, what to forget, and how to update the memory, protecting the gradient signal much more effectively.
GRUs were similar, but a bit simpler, right?
Yeah, GRUs streamlined the gating mechanism, fewer parameters, often computationally cheaper than LSTMs, but frequently achieved very similar performance on many tasks. They were really successful.
They solved the memory problem, the gradient problem. So what was the catch? Why did we move on again?
The catch was inherent in the R of RNN, LSTM, or GRU, the recurrence. They must compute the state sequentially. $HT absolutely depends on like 1 for.
Step at a time.
Always. Every word has to wait for the processing of the word before it. You cannot calculate the state for word 50 until you've calculated it for word 49, and so on, all the way back to the beginning.
And that means no parallel processing across the sequence.
Exactly. You couldn't throw the massive parallel power of modern GPUs at the sequence length. You could parallelize across batches of sequences, but not within a long sequence. And as we started wanting models to understand entire documents or books, that sequential bottleneck became the ultimate limiting factor.
It was just too slow for very long context.
Precisely. That sequential dependency, that inability to parallelize over time, was the architectural wall that demanded the next revolution.
Okay, so RNNs, even LSTMs, hit a speed limit because of their sequential nature. The transformer architecture, famously introduced in the paper Attention is All You Need in 2017, aims squarely at that problem, right? Speed through parallelism.
That was the absolute core goal. Eliminate recurrence, unlock the hardware.
How did they do it? What replaced the recurrence?
Attention. Specifically, self-attention, sometimes called intra-attention. The key idea is that to compute the representation for any given word in the sequence, the model can directly attend to or look at every other word in the sequence, all at the same time.
Simultaneously. No waiting.
No waiting. Think about the path length. In an RNN, for information to flow between word 1 and word 100, the signal has to travel through 99 sequential steps.
Right.
In a transformer with self-attention, the path length between word 1 and word 100 is 1, a single step.
Yeah.
They are directly connected through the attention mechanism.
Wow. Okay, so it reduces the path length to constant time, regardless of distance.
Exactly, and that's what enables massive parallelization across the sequence length.
So how does this self-attention actually work? You hear about query, key, and value Q, K, V.
Right. QKV is the abstraction. It's helpful to think of it like a fast information retrieval system, almost like searching a database, but applied to the words within the sequence itself.
Okay, walk me through it. Let's say we have the sentence, the tired cat slept, and we're calculating the new representation for the word cat.
Okay, so for the word cat, the model first generates 3 vectors derived from its current embedding: a query Q vector, a key K vector, and a value V vector.
What do they represent?
The query is like the question cat is asking, what information in this sentence is relevant to understanding me right now? The key vector for cat, and every other word also generates its own key, acts like an index label for the information cat holds. And the value vector for cat holds the actual content or meaning cat contributes.
So cat sends out its query.
And it compares that query vector to the key vectors of all words in the sentence, including itself, the tired cat slept.
How does it compare them?
Usually with a dot product. A high dot product between the query of cat and the key of, say, tired means tired, is highly relevant to understanding cat in this context.
Okay, so you get these relevance scores.
Exactly. You get a score for how relevant each word's key is to cat's query. These scores are then scaled, usually divided by the square root of the dimension of the key vectors, score-to-score stability, and then fed through a softmax function.
Softmax turns them into probabilities, right? They all add up to 1.
Precisely. So now you have attention weights. Maybe tired gets a high weight, say zero 0.6, slept gets a moderate weight, 0.3, and V gets a very low weight, 0.1.
And then the value vectors come in.
Yeah, you use those attention weights to compute a weighted sum of all the value vectors in the sentence.
Yeah.
So the new representation for cat becomes mostly a combination of the value of tired and the value of slept, plus a little bit of its own value and the value of long.
Ah, so its new representation is a blend of itself and the things it decided were most relevant to it.
Exactly. And the crucial part is this whole QKV calculation, the dot products, the softmax, the weighted sum of values, it happens in parallel for every single word in the input sequence simultaneously. That's the source of the massive speedup.
And transformers don't just do this once, right? There's multi-head attention.
Right. Doing it just once might limit what kind of relationships the model can focus on. So multi-head attention runs several of these self-attention processes in parallel, typically 8, 12, 16, or even more heads.
Each head doing its own QKV calculation.
Yes, but with different learned transformations for the Q, K, and V vectors. So each head can learn to focus on different kinds of information or relationships. Maybe one head learns syntactic dependencies, another focuses on semantic similarity between verbs, another tracks pronoun references.
And then the results from all heads are combined.
Exactly. They're concatenated and pass through another linear transformation, creating a final output vector that incorporates insights from all these different representation subspaces. It gives the model a much richer, more nuanced understanding.
Okay, that makes sense. But the original transformer just used fixed sine and cosine waves for positional information, right? Did that turn out to be enough?
It worked surprisingly well, but it had limitations, especially for tasks needing really fine-grained understanding of relative order or structure over very long distances.
Like music.
Music is a prime example. Absolute position, this is the 500th note, might be less important than relative timing. This note comes 8 beats after that one. Or relative pitch. This note is a perfect fifth above the previous one. This led to the development of relative positional self-attention.
How does that work?
Instead of just adding an absolute position signal, the model learned separate embeddings that represent the pairwise distance or relationship between the two tokens being attended to. So when calculating the attention score between word I and word J, it also considers the relative distance, IJ.
Ah, so the distance itself gets encoded.
Right. And the music transformer paper showed how crucial this was. Generating coherent music over minutes, thousands of time steps, was really hard for standard transformers.
Yep.
They lost track of long-term structure.
But with relative attention.
By explicitly incorporating relative timing embeddings and relative pitch interval embeddings into the attention calculation, the music transformer could generate long, complex pieces with remarkable internal consistency, harmony, and melodic structure. It vastly outperformed baseline transformers and LSTMs, showing that for some domains, encoding relationships is key.
That's fascinating. Now, shifting gears slightly, how does this idea of architecture connect to more structured NLP tasks, like parsing a sentence into its grammatical structure? You mentioned something about local versus global normalization.
Ah, yes. This is another important architectural insight, though it predates the transformer slightly. It's highly relevant. It relates to how models make decisions in structured prediction tasks, like deciding the grammatical tag, noun, verb, adjective for each word. The issue is called the label bias problem.
Label bias, what does that mean?
It happens in models that are locally normalized. Imagine the model is tagging words one by one. At each word, it calculates probabilities for all possible tags, noun, verb, etc., using a softmax function. That softmax normalizes the scores locally, forcing them to sum to 1 at that specific word based only on the information seen so far.
Okay, seems reasonable. What's the bias?
The bias is that once the model makes a high probability decision locally, for example, this word is definitely a verb, it's very hard for it to revise that decision later, even if subsequent words strongly suggest the initial decision was wrong. The local normalization kind of locks in the choice too early.
Give me an example.
Consider, the man saw the boat with the telescope. When the model hits the second saw, based on just the man saw, it might strongly prefer the verb tag, but later, with the telescope, makes it clear that saw was probably a noun, the tool. A locally normalized model struggles to backtrack because the probability for verb was already normalized and committed high early on. It gets biased towards paths with high local scores, even if the global path is wrong.
So it can't easily correct itself based on future context.
Exactly. The solution is global normalization, often implemented using a conditional random field, or CRF, layer on top of the network.
How is that different?
A globally normalized model doesn't use softmax at each step. Instead, it calculates a score for the entire sequence of tags for the whole sentence. It considers all possible tag sequences and finds the one with the highest total score.
So it looks at the whole picture before deciding.
Precisely. This allows information from the end of the sentence to influence decisions made at the beginning. It can see that tagging saw as a noun leads to a much better overall score for the entire sentence, even if verb looked good locally. This makes globally normalized models strictly more expressive.
But I assume it's slower. Calculating scores for all possible sequences sounds computationally expensive.
It is significantly slower, yes. But for tasks like dependency parsing or named entity recognition where structure is paramount, the accuracy gains are often huge. Those state-of-the-art parsing scores, like getting 94.61% accuracy on identifying grammatical dependencies, often rely on these globally normalized approaches to resolve ambiguity correctly.
Okay, so we've built these incredibly powerful transformer models. They can process huge amounts of context in parallel, learn complex relationships, but just training them to predict the next word on the internet doesn't automatically make them useful or safe, does it?
Not at all. That's the core problem of alignment. A base LLM, trained purely on next word prediction, is just a statistical pattern matcher. Its objective function is often fundamentally misaligned with what we actually want from it as users. We want it to be helpful, honest, and harmless.
It might predict statistically likely text that's biased, nonsensical, or even dangerous.
Exactly. So after the massive pre-training phase, there's a crucial second phase, alignment or post-training, to steer the model's behavior.
And the first big step in that is usually instruction tuning.
Right. Instruction tuning, often called supervised fine-tuning, or SFT. This is where we start teaching the raw, pre-trained LLM how to follow instructions, how to behave like a helpful assistant.
How does that work? Do you need a whole new kind of training?
Not really a new kind, but a specialized data set. We curate or collect a data set of maybe thousands or tens of thousands of examples. Each example is basically a prompt or an instruction paired with a high-quality desired response.
Where do these examples come from?
They can come from humans writing them, or by repurposing existing NLP data sets, question-answering data sets, summarization tasks, translation pairs, and formatting them into this instruction response template. Translate this sentence, summarize this text, explain this concept.
And you fine-tune the pre-trained model on this data set.
Exactly. And importantly, you typically still use the standard language model loss, predicting the next word, but only on the response part of the examples. You're teaching it. Given this instruction, this is the kind of text you should generate next.
Is this expensive compared to pre-training?
Oh, much, much cheaper. It's a tiny fraction of the computational cost, maybe just a few epochs on this much smaller curated data set. But the goal isn't just to memorize these specific instructions.
It's to learn the general skill of following instructions.
Precisely. The hope is that the model generalizes.
Mhm.
It learns the underlying pattern of, okay, user gave a command. My job is to comply helpfully and accurately. You test it by giving it completely new instructions it didn't see during SFT. That's how you know if it worked. It transforms the raw predictor into something you can actually interact with.
Okay, so SFT teaches it how to follow instructions, but what if there are multiple ways to follow an instruction and some are much better, safer, or more aligned with human values than others?
Excellent point. SFT alone doesn't necessarily teach the model about preferences or nuances. That's where the next stage often comes in. Learning from preferences, usually human preferences.
This is where reinforcement learning from human feedback, RLHF, comes in, right, with things like PPO.
Traditionally, yes. RLHF was the standard approach. The process usually involved collecting data where humans compared two different model responses to the same prompt and indicated which one they preferred.
Okay, output A is better than output B.
Right. Then you'd use this preference data to train a separate reward model. This model learns to predict how much reward or preference score a human would likely give to any potential model response.
So you train a model to predict human judgment.
Exactly. And then you use that reward model within a reinforcement learning algorithm like PPO, proximal policy optimization, to fine-tune the actual LLM. The LLM tries to generate responses that get a high score from the reward model.
That sounds complicated. Two separate models, RL algorithms.
It is complicated. Training the reward model effectively is hard, and PPO itself is notoriously complex, unstable, and very sensitive to hyperparameters. It requires a lot of compute and careful tuning. It was a major bottleneck.
So is there a better way?
Well, a much simpler and often more stable approach that's become very popular is direct preference optimization, or DPO.
DPO. How does that work? Does it still use preference pairs?
It still uses the same preference data: prompt, winning response, losing response. But the breakthrough with DPO is that it found a way to bypass the need for training an explicit reward model and bypass the complex RL algorithm like PPO.
How on earth does it skip the reward model?
It's based on a clever mathematical insight. There's a theoretical connection, often derived using models like the Bradley-Terry model for preferences, that links the optimal LLM policy directly to the probabilities derived from the preference data. DPO found a way to derive a loss function that optimizes the LLM directly based on this connection.
So instead of learning a reward function and then using RL to maximize it, DPO found a loss function that directly makes the LLM more likely to produce the winning response and less likely to produce the losing one.
That's exactly it. It transforms the preference learning problem back into a simple supervised learning problem. You just calculate this DPO loss based on the prompt, the winner, and the loser, and update the LM as weights using standard gradient descent.
Wow, that sounds much simpler and more stable.
It generally is. It avoids the instability and complexity of training a separate reward model and running RL. You just need the preference data and the LLM itself. It's a single-stage optimization process.
So DPO is essentially a more elegant, direct way to inject human preferences and values into the model's behavior.
Precisely. It's become a very powerful and widely used technique because it's simpler, more stable, and often achieves comparable or even better results than the older RLHF PPO pipeline. It really shifts the focus back to collecting high-quality preference data, which is arguably where the human insight really lies.
Yeah.
Hashtag outro.
Wow. Okay, what an incredible technical journey we've just traced. We started way back with the problems of n-grams, that sparsity issue.
Right, which led us to the breakthrough of semantic vectors, word embeddings like word-to-vec and glove, capturing meaning through geometry and even vector math.
Then we hit the sequence modeling era with RNNs, and that almost show-stopping gradient crisis, vanishing and exploding gradients.
Yeah, a problem tackled first by clever hacks like clipping and regularization, but truly solved architecturally by LSTMs and GRUs, though they still had that sequential bottleneck.
Until the transformer arrived, shattering that bottleneck with self-attention, enabling massive parallelism and scale.
And we saw the refinements, too, like relative positional attention being crucial for long-range structure in things like music.
And finally, bringing it all together, we looked at how these giant, powerful models are actually tamed and aligned, first through supervised fine-tuning, teaching them to follow instructions.
And then through incorporating preferences, moving from complex RLHF pipelines to the much more elegant and direct approach of direct preference optimization. DPO.
Yeah, the DPO insight seems really key. It feels like the whole story from vector math to relative attention to DPO, it isn't just about making models bigger, is it? It's about finding these really clever, fine-grained mathematical mechanisms.
Absolutely. It's about perfecting the subtle structures, the mathematical relationships, like accurately encoding relative positions or finding efficient ways to optimize directly on preference data. These are the things that allow models to achieve coherence and align with our goals over these vast computational scales.
Which leads us to a final thought for you, our listener. If relative positional attention unlocked long-term musical structure and DPO gave us a much cleaner path to alignment, what other subtle mathematical mechanisms or architectural insights might be out there waiting to be discovered? Could the next big leap towards truly coherent, maybe even agentic AI, come not just from more data and bigger chips, but from finding the next elegant equation? Something to think about.